A very good morning to all of you. My name is Rohith Thundathil. I'm a postdoc at the German Research Center for Geosciences and the Technical University of Berlin. My co-authors, Karina and Jens, are already here. So our research focus is on the assimilation of GNSS products into the weather model for severe weather prediction. So we mainly focus on the tropospheric gradients in this presentation. So as you already know, the Zenith Total Delay observations are widely used in the operational research forecast centers now, and this mainly contains the integrated water vapor information about the stations. And on top of that, the gradients is a new observation type which is being implemented in operational research forecast agencies right now. And we are focusing on the gradient observations in this presentation, which gives you the moisture distribution of the region. And the direction of the gradients points from a dry to a wet region in the observation. So as you can see, there is a direction vector. So it is mostly related to the vector quantity rather than the Zenith Total Delays, which is a scalar quantity. So this gives you an idea about how the dynamics of the weather of the moisture is present in a region. So we have recently developed a gradient operator in the weather research and forecasting model, and that has been tested. And we have published this online in two of our journals. My colleague Florian and myself, we have two publications on this. The second publication is regarding the assimilation impact of the gradient observations. Now, how do you see the gradient inside a model? So this is how we detect the gradient observation impact in a model. On the left-hand side, you can see the gradient observation impact, and the right is the Zenith Total Delay. So the main difference in this observation type is that, as I said, it's a vector quantity. It has a dry and the moist side. So when we compare the Zenith Total Delay observations and the gradient observations, the main difference is that the Zenith Total Delay observations gives you the amount of water vapor from the surface level. And the gradient observations is a collecting quantity which redistributes the moisture information from the lower troposphere of the atmosphere. So you can see the impact is mainly on the lower troposphere side, and for the Zenith Total Delay, the impact is on the surface level. And yes, the profile information, from the profile information you can see that the most of the impact is on the higher eta levels, which is the model levels. So our weather model is a weather research and forecasting model. We have configured for a 11-kilometer model, and this the GNSS observations were taken from the benchmark study, which was conducted in 2013 by Thundathil, who is already here. And we have collected over 250 GNSS stations which cover over Germany, Czech Republic, Poland and Austria. So coming to the data assimilation part, we need the data into the model. So we limited the type of observations which are used in the model to conventional observations such as radiosondes and surface observations to initialize the model regarding the profile impact as well as the surface impact, and which was added on top of the Zenith Total Delay observations. So we have three primary experiments which focuses on the data assimilation of Zenith Total Delays and the gradients. And the first base experiment we call the control experiment, which incorporates the assimilation of synop stations and the radiosonde stations. And the next is the impact experiment, which includes only the Zenith Total Delays on top of the control experiments. And the third experiment is the impact gradient experiment, which is also called ZTD graph, which incorporates the Zenith Total Delays and also the gradients. So these are the primary experiments which we focused on. And this is the data assimilation framework which we developed at the GFZ. This incorporates the assimilation of the weather research and forecasting model, which is initiated by the ECMWF analysis. And the assimilation frequency is every 6 hours, which can be varied according to our interest. Although the data is available every hour, we are using the assimilation every 6 hours since this is a prototype and it's conducted for 2 months of time. So we have a large observation data set and analysis data set for more statistical confidence. So we have 3 experiments: the control, the ZTD, and the ZTD graph. So coming to the first results. So this is a control experiment result with we have around 250 GNSS stations, and the time series gives you an idea. This is a standard deviation with respect to each of the GNSS stations, and for the 2 months time period, which includes around 240 data assimilation cycles. And you can keep an eye on the mean of the standard deviations for the ZTD on top, the north gradient and the east gradients on the lower rows. When we assimilate the Zenith Total Delays, we can see a drastic decrease in the standard deviations for the ZTDs and the north gradients and the east gradients. So this is the scenario where we assimilate only the ZTDs. So when we add the gradients, what we observe is that we find a sudden dip in the not only the gradients but also the ZTD components as well. So in a nutshell, we observed an overall impact that when we add the gradients on top of the ZTDs, we increase the RMSE reduction slightly more, most prominently on the gradients and also on the ZTDs. So it has a synoptic effect, a symbiotic effect. And we have analysis with respect to the ERA 5, which we compared around 1,220 profiles. We compared with 5 stations, which was distributed over Germany, and we found out that when we compare the ERA 5 profiles, we find an improvement in the lower troposphere region. So this is the magic of the gradient observations. We improve the lower troposphere region, which was not accomplished by the ZTDs. And when we see the forecast for 5 hours, we see that the red is the Zenith Total Delay and the gradients analysis. We find out the analysis improves and stays in the forecast for almost 5 hours. So this was the initial improvements. And now next we conducted a sensitivity analysis, which we distributed the stations as a dense and a coarse network. And we found out a new magic in the ZTD gradients. We found out that the Zenith Total Delay and the gradients improved the RMSEs. But what we found out is that a coarser Zenith Total Delay gradient observation network has almost similar impact to a ZTD observation network, which was a dense observation network. So this we compared with the analysis increments and found out that most of the analysis increment high impact regions are captured by the Zenith Total Delay observations, which was assimilated in the coarser resolution as well. And next we compared the ERA 5 and we found out that the 2 profiles, the red and the blue, which is the blue is the ZTDs with the 0.5 degree dense network, and the red is the 1 degree network, and they almost coincide with each other. So this is a major improvement, and we can see that the Zenith Total Delay and gradients can be assimilated in regions where we have very few GNSS networks, and it results in the same improvement as ZTD networks. And the next study we started, we are currently ongoing with this typhoon simulation over Taiwan, and we are assimilating GNSS stations over Taiwan and also stations from Japan and islands over Japan as well. So in this simulation, we are focusing on extremely severe weather events, and this typhoon in Taiwan was called Koinu, and this is a severe weather event, and which happened in October 2023. So the typhoon hits the Taiwan coast on the 4th of October. This was a control run we initiated with the Weather Research and Forecasting Model. And now our next step is to assimilate the ZTDs and gradients on top of these measurements and find out the improvements. So we have well accomplished with the track of the cyclone. Now we have to see the improvements of how much water vapor, and the analysis is related to the improvements. On the left side you can see the reflectivity, where you can see the water vapor content, and on the right side you can see the water vapor mixing ratio improvements. So yes, to conclude, the tropospheric gradients contains additional information, which is clear now, and the assimilation of ZTD and gradient observations within a sparse network gives you more accountability of the improvements rather than a densely ZTD observation network. And from the statistics over 2 months, we found out the improvements with respect to the GNSS stations in the era 5. We found out that the gradients have clearly a promising impact. And in future, we are trying to assimilate the observations with respect to an ensemble-based data assimilation network system, and which will probably improve the forecast. So our results have been published in the GMP, so you can read improvements and also download the code changes in the weather research and forecasting model, so the users can use the model and find out the impact yourselves. And yeah, thank you for your attention. And this is a AGU session which is coming in December about the assimilation experiments of the GNSS session for atmospheric sensing. Thank you.